Now when it comes to making videos on electrical theory, I try to avoid it for two very good reasons. Now the most obvious reason is of course that most of the time I've got no idea what I'm talking about. I'm probably going to get it wrong and I don't want to mislead anybody. But the second reason, and one that's perhaps more important to me, is that John Ward said that if he ever did it again he was going to send round a van full of lads to break my legs.
Like weak, very soft, driving to the ground.
So as per usual, I've just spent the last 20 minutes waffling on about nothing, and we haven't even switched our transformer on yet and tested it. So as you saw earlier, the piece of equipment that we're looking at today is a transformer. It has a 230 volt primary input and it has a 110 volt secondary. And because it's an AutoTransformer, there is no isolation between the primary side and the secondary side of the transformer, which can make it just that little bit more dangerous. Now as a general rule in my videos, I don't give out health and safety warnings. I don't think they're very effective at stopping people from getting injured. And I'm also a great believer that, unfortunately, we tend to learn the hard way. But just for today I am going to give a warning that we're working at 110 volts and 230 volts. Those voltages are quite high enough to give you a really nasty electric shock and could even prove fatal. So back in the day it certainly wasn't uncommon to take various high voltage measurements using an oscilloscope, and you know, here's a typical probe here. They do come in a variety of voltage ratings and also attenuation factors, so it's not really a problem actually probing fairly high voltage circuits. You can do that with the right equipment. Now of course when we make a voltage measurement using an oscilloscope we stick the pointy end on one side and the earth clip on the other, and it's actually the earth clip here that causes us all the problems. Now the reason it causes such a problem is because the earth clip on your oscilloscope, unlike a voltmeter or something like that which is likely just to be floating, the actual black connection, the earth lead on your oscilloscope probe, it actually goes back through your oscilloscope and it goes back to the earth pin on your plug. So all the measurements that you take are kind of reference, well they're not kind of, they are reference to earth. Now that can cause a problem because if you actually clip this onto a live part of your circuit, say the live supply, you're actually going to be putting a direct short circuit between the live supply and your earth. So if you're very lucky you're just going to get a big bang, the power will go off and you will probably end up frying the earth connection on your scope. I'm going to say most of us have done it at one point or another. Well, you have if you've been in industry long enough. Now of course some people are going to say, well I'm not stupid, I'm not going to connect the earth clip of my oscilloscope to the live side of my main supply, why would I do that, that's stupid. I'm going to be smart and connect it to the neutral. Now the problem with connecting the ground clip on your scope probe to the neutral side is, well although we call it a neutral connection on the equipment, if you actually follow it back it actually becomes the same thing as ground. So in many situations neutral and ground are actually effectively the same thing. So the problem is, if you clip on a scope probe, some of that current, rather than going through the neutral connection, it's going to go through your scope probe. But the problem that you'll have is that this is only a little thin wire, so one thing that will happen is probably this wire will burn out. Again, that's not good. But the other thing that will happen is if you've got a fairly modern house with a modern consumer unit, it will actually detect that not all of the live power is coming back down the neutral connection. It'll detect an imbalance and that residual current circuit breaker will trip out and all the lights will go off, so that's not very good either. So having established that it really is a pretty bad idea to attempt to connect the ground connection of our scope to either the live or neutral of our main supply, how do we make our measurement? Well, the first method that you used to employ, which was really stupid and very dangerous, is what you could actually do is you could actually disconnect the earth wire from the oscilloscope, so that would remove its ground reference, and then you could actually clip the ground connector of your scope probe onto the neutral side of the mains. Now, I say that's a non-prescribed method. It's a really dangerous, really stupid method, because if you get it wrong, the body of your oscilloscope would become live. Now the second way, and the prescribed way of connecting your oscilloscope to a mains circuit, is to actually use something called an isolation transformer. And I'm sure if you Google isolation transformers you'll find lots of YouTube videos telling you how to do that. However, in certain situations it's not always practical to use an isolation transformer. So what we're going to be doing today is we're going to be using a third technique, which is using a special type of oscilloscope probe called a differential probe. So this is the differential probe that I'm going to be using today, which is manufactured by Sig. At the top of the probe here we've got the high voltage connections, and it's also got the voltage specification on it, and it says here that it's a category 2 device, and we can use this probe up to 1300 volts maximum. And then lower down on the unit we've got an attenuation factor where we can set it to times 50 or times 500, which is effectively it's dividing by. At the moment I've got it set to the 500. And the model number is DP10013. I can't remember how much these are off the top of my head. I think they're quite expensive, maybe £200 or £300. But if you are seriously interested in taking mains measurements, I would actually say that a differential probe is absolutely a must-have item these days. So for the input to the differential probe, I've actually just got some test leads plugged into it at the moment, but you can plug crocodile clips and things like that. In fact, this MIXIG probe comes with a kit of parts that allow you to connect it to most things. So this is the live high voltage end, and then it's got a couple of connections at the bottom. So one of the connections here just goes straight into channel 1 input of the scope, just like a conventional scope probe, and the other connection here is actually a USB connector, but it only uses a USB to supply power. Now of course most of us are going to be familiar with using an oscilloscope to measure voltage. But of course it's massively useful to also directly read your currents that are flowing around in a circuit. Well, to do that I'm going to be using this Handtech, and it's an AC-DC current clamp. So the way you actually use this is, if you want to measure the current in a wire or something like that, we just open up the clamp and then you put the wire of the circuit through the clamp and close it back up. I think you may have seen me using this current clamp before, and I've got to admit I really do like it. These Handtech ones are relatively low cost and they do seem to work really well, so I definitely recommend them. So I'm also going to be using a variety of test adapters that I've made up, and these just allow me to actually change the gender of various types of main sockets and plugs, and because I've got them stacked up with these banana plugs, it makes it very easy to actually cut into the supply circuit and connect in our test gear. Unfortunately, you've got to be a little bit careful using banana plugs, and especially some of these type which aren't fully insulated. They've got the live prongs exposed, so if you have something half clipped in like that you could get an electric shock. But again, I'm used to working with mains equipment. I am quite careful, and that's what we're going to use, but again, take precautions. Another piece of equipment we're going to be using today is this plug-in power energy monitor plug. Now these are great because they will actually show the current and the wattage and the voltage, and when you're working on repairing a piece of equipment it's really useful to know if it's actually drawing the right amount of power from the main supply. So it's really useful to have one of these plugged into your bench at all times. So I'm just going to plug in our energy monitor plug because it's just useful to keep an eye on our main supply, because it does vary quite a lot here. So you can see that the mains voltage coming out of our socket here is actually 241 volts. Now nominally in the UK it should be 230 now, but because I've probably got quite an old supply transformer, it's given around 240, and it's not untypical for my voltage here to be, well, 251, 253. It tends to be quite high here, so actually having a voltage region of 240 is pretty low for me. So you can see that my domestic supply, it's around 241 volts at the moment. So I'm just going to get, and I'm going to connect up the differential probe to the output from our step down transformer. And we'll plug our transformer in. So you can see there, for our 241 volt input, our transformer's stepping down to 123 volts output. So here's our 241 volt input, and our output is it's 123 volts, 123 volts at the moment. 241 divided by 123 equals 1.959 to 1. So for every 1.95 windings on our primary, we have one winding on our secondary. So you see we've got a stepping down ratio there. So this transformer is actually described as being a 230 to 115 volt step down transformer. Now unfortunately my main supply voltage is a little bit higher at 241, but what we can do is we can get a rough guess just using this transformer ratio here. So basically if we type in 230 volts if our supply was 230. Divide that by 1.959 equals. So I suspect that it's more likely our transformer would be giving out 117 volts if it was actually connected to a 230 volt supply, and that's you know, slightly more correct. But 122 volts unloaded, that's fine. So according to the manufacturer's instructions, not only can this transformer step down to 110 volts, if we actually took this transformer to America, we could use it to step up from 110 to 230. So the way that you actually do that is you just select the 100, well, I say 110, it's 115 volt on here. So I've just moved over the voltage selector to 115. So what we'll do is we'll power this up using the VYUAN, and again we'll just check what the output is. Just for convenience, I'm using our plug-in energy monitor. So we'll switch the transformer on, and hope you can see that we're getting 230.3, and the input to the transformer to the primary is 115 volts. So in terms of voltage, it's absolutely spot on, no problem. So not only will our transformer step down from 230 to 110, it's also quite capable of stepping 110 back up to 230 volts. If you look at the Amazon listing for this transformer, it describes it as being a low inrush transformer. Now for a conventionally wound transformer, the inrush current can be as much as 10 times the full load current, and for a toroid it can be as much as 60 times the full load current. Well, just for giggles, I thought it might be quite interesting to try and take a measurement of the inrush current. So what I've done is I've got our differential probe here. Apologies for the rat's nest. And this is just connected to the incoming mains supply. So we're actually supplying the transformer again with 240 volts. So the scope is actually showing in yellow here. That's just the incoming mains. And then again on the incoming side of the transformer, on the primary side, I'm measuring the current using this clamp meter. So all I've actually been doing is I've set up the scope to trigger on the incoming mains when it detects some mains, and you've got to switch it on and off like this. You just keep switching it on and off, and using the scope in a single sequence, I've just been capturing some waveforms. You've actually got to do it repeatedly because of course when you flick the switch on you don't quite know at what part of the main cycle you are, so it's kind of pot luck. Anyway, I've been doing it for 5 or 6 goes, and I think the highest inrush current I've managed to capture so far, it's around 99.2 amps. So that's not exactly what I would call low inrush, but the inrush current doesn't actually last very long. For here, it's, you know, it's just less than half of a main cycle. Now I'm sure it's going to take me quite a few goes to actually try to catch the main cycle near its peak, but we'll have a go. Okay, 70 amps that time. Oh, probably at the zero crossing point there. Oh, we got one. Okay, 106 amps, that's a new record. Okay, let's see if we can beat that record. Oh, we got lucky again. Is that another 106? Oh, nothing there. Nothing again. $104 amps. And 106 amps. So it seems that typically we're getting a reading of around 106 amps. So just for my own benefit, I think I would like to think about this transformer inrush issue just a little bit more. So I'm just going to roughly draw our transformer here. And this transformer is an iron core one, which I've just drawn there. And I've only drawn one side of our transformer here, just the primary, because that's all I'm interested in at the moment. Now if you think of what a transformer is, all a transformer is, it's a long length of wire that's been wound into a coil. Now because this is quite a long length of wire, it does actually have some resistance to it. So what I'm going to do is I'm just going to kind of loosely scribble this in here. So just imagine this. This is a resistor, and this resistance is it's representing the DC resistance of the winding, because of course it is a long wire, and nothing is a perfect conductor, and everything has a little bit of resistance. Now that resistance value, it's going to be governed by two things. One thing it's going to be governed by is the length of the wire. So if we've got a really long wire, it's going to have relatively high resistance. If we have a short wire, it's going to be much lower resistance because there's less material for the electrons to try to get through. Now of course the other thing that's going to affect the resistance of the wire is how thick it is. If you have a very thin wire there, that's going to have a relatively high resistance. In fact, worst case, if we've got a thin long wire, that's going to have high resistance. So if you've got a long wire, what you want to do is you want to use a really big thick wire, something that's got a lot of copper in it, a lot of thickness to it, because that's going to have a low resistance. So our transformer here, it's nominally going to be connected to 230 volts, isn't it? So the actual, if we look at the peak voltage, because obviously that's RMS, that's the equivalent, heating equivalent of a DC circuit, the actual peak voltage will be somewhat higher. Let's call it 330. So the peak voltage that this transformer could see, if we actually switch it on here when the mains is at the top of its cycle, this transformer, for that instance, it's got 330 volts across its winding. So when we actually switch the power on, we get an electrical field forming here. We get current flowing. Because we have a current flowing in a coil of wire, it starts to magnetise the core. But the problem we have here is that this core material, it does actually resist becoming magnetised. It's not a perfect material. So what will happen is that we have a very high current flowing, but the core of the transformer can't instantly accept that magnetic core. It takes time to magnetise. So what's really happening is this isn't really acting like a normal magnetic circuit. What will happen is the transformer will saturate. So rather than acting like a coil of wire, it actually just starts acting like a long string, a long piece of wire. Now the only thing that's limiting the current flowing in this now long length of wire is this resistance here. So at switch on, the thing that really just limits your inrush current is it's actually the DC resistance of your transformer coil here. Now that's not quite true, because you've got to remember that this transformer doesn't just work in isolation. If you take it back far enough, it's actually connected to another transformer, which is your supply distribution transformer back here again. And likewise, this transformer has a resistance, so we'll draw that there. And also the wiring between my house here, this is my house with my transformer in it, we've got some resistance in the wiring between my house and actually the distribution transformer. So we've got another resistor there. So what's actually limiting the inrush current? It's the winding resistance plus the supply impedance, which is the wiring, plus the transformer impedance back there from the distribution transformer. And we can actually crudely measure some of that and see if we get the right kind of figures. So let me go ahead and have a go at that, and let's just see what the figures come out at. I don't know if it'll work, I'm just interested to see myself, so let's do that. So here's our step down transformer, and I've just got this plugged into a little extension lead here, a very short one, and it's got my def adapter connections on it and a plug, and of course it's got these connections on it so we can plug various bits of test equipment in it and take measurements. From the primary side of the transformer, this is our electrical circuit, so basically the live and neutral here are going to connect across the primary of our transformer. What I'm going to do is I'm going to measure the resistance of this, so I'm not just measuring the resistance of the transformer primary, I'm also measuring the resistance of our wiring, and it's probably going to be quite a low reading. So to measure the resistance of our primary circuit, we're going to use this fluke meter, and this fluke meter is a little bit special in that it's designed to test electrical installations, so it has some rather specialist functions that you wouldn't find on a normal bench meter. Now before we take our resistance of our transformer, it's actually going to be a very, very low reading we're going to get, so we don't want the resistance of the test leads here to actually interfere with the measurement we get. So we've got to null them out. So we clip them together, and I think we press test on this meter. And I think I release that button, and I think I hold it down, and it zeroes out. And I think if I press test again, okay, so that's coming up 0, 0, 0. So I get the leads now, I'm going to clip them across there. I'm going to make sure we've got a good connection. And we just measure the resistance, press test again. So the resistance of our transformer primary and the connecting wires is coming up there as 1.98 ohms. So now that we know the resistance of our transformer, its connecting windings, well, the bit that we don't know is we don't know what the supply impedance is. So we've got the wiring now between my house, well, the internal wiring in my house here, first of all, that's going to have a resistance to it, and then we're going to have a resistance back to the I don't know, I live out in the country here, so we've got these big transformers that are strapped to the sides of kind of like telegraph poles. They call them pole pigs in America. So we've also got the supply impedance back to the pole pig. Well, I'm going to use a special function on this flute meter to actually measure something called Z-loop. Now, I think that Z-loop, I'm not particularly familiar, I'm not an electrician, I think the Z-loop reading is actually between the earth and the live conductor. But because of the type of electrical installation that I've got in my house, which is PME, my earth wire and my neutral conductor, they're effectively the same thing. So I'm going to try to use this flute meter to measure the impedance of my supply here. So I'm going to go ahead and I'm going to plug our tester into the same socket that's been supplying our transformer all the time. And all we're going to do is just going to press the test button and it'll go away. It takes a few seconds to do the test, and it's going to give us both the loop impedance, it's going to give us the resistance of our conductors here, and it's also going to give us something called the PFC, which is the perspective fault current. So the meter's come back and it's reporting two values. So it's saying that the resistance between our live conductor and earth is 0.67 ohms, and based on that resistance it's also measured the supply voltage, and it's saying that absolutely the maximum current that we could pull from our installation here in my house is 361 amps. Now of course you couldn't really pull 361 amps because, well, you probably could momentarily, but obviously we've got circuit breakers that would trip out eventually, and the house is probably protected by a 100 amp fuse. Of course fuses and circuit breakers don't trip instantly, so for very short times you could probably pull 361 amps quite easily. Anyway, the reading that we're interested in here is 0.67 ohms. And the way that I'm just going to try to calculate the peak current now is I'm just going to very crudely use Ohm's law. So our nominal supply voltage is around 230. What we're going to do is we're going to take our 0.67 and we're going to add that to 1.98 ohms. So we're just doing V over R, of course, equals I. 230 divided by 0.67 plus 1.98 equals 86.79. Now I think that 86.79, that's going to be an RMS value. Now of course when we used our oscilloscope we were looking at the peak, so I'm just going to convert that to peak by dividing by 0.707, and that gives us a maximum inrush current there of 122 amps. Well, I think I was measuring 106, but I suspect that 122 might be in the ballpark. Now I've just done this as a little bit of an experiment for my own interest. I'm not sure if I've got it right, I'm not sure if I've got it wrong, but I would be interesting to hear from you guys any comments. So do leave it in your comments. When it comes to transformers, I think there's two parameters which are perhaps the most important, and those are voltage regulation and also the efficiency of the transformer. Now voltage regulation is actually quite simple. All it means is it's the amount that the voltage on the secondary will fall by as we start to connect a load to it. So the more current we draw from the transformer, the more the voltage will drop. So you can imagine if we connect a piece of equipment to our transformer and that piece of equipment is expecting to be supplied with 110 volts. Well, if we actually load up that transformer enough, that voltage is going to drop, and maybe it'll drop from 110 volts, maybe to 100 or less. Well, the piece of equipment we're trying to run might not work anymore. It might not work at 100 volts, it could stop working. So that's why voltage regulation is important. Now there's no such thing as a perfect transformer. The voltage from the transformer will always start to drop, and that's because internally the transformer has some losses. Now when it comes to loading a transformer, the most important losses are what they call copper losses, and they're to do with the cross-sectional area of the winding and the amount of wire in the winding. But for a good, well-constructed transformer, we would expect the percentage voltage regulation to be within, I don't know, 2 to 5%. So typically when we measure the voltage regulation of a transformer, what we have to do is we have to take the open load voltage across the transformer, so that's the voltage on the transformer secondary when there is no load connected to it, and then we have to take the voltage across the primary when it's connected with its full load. So I'm going to set up our test now so that we can show the voltage regulation of our transformer, but unfortunately I'm not going to be able to do it at the full load because I can't actually arrange a load of around 1000 watts, which is what we would need. The most I can provide here is 500 watts, so we're not actually going to show the full load regulation characteristic. However, I think what you're going to see is close enough, and you're certainly going to get an idea of how to do it. So as part of our voltage regulation test on this step-down transformer, we need to keep the primary voltage that we're supplying to the transformer, we need to keep it absolutely steady, because as we load up this transformer here, it's going to tend to pull power from the mains, and because the mains wire is resistive, the voltage is going to drop. Well, we're going to use the VYUAN transformer here. As the voltage starts to drop, we're going to tweak it back up, so we're going to maintain 230 volt supply to our device under test here. So the VYUAN that I'm using, you can see it does have a voltmeter on it, but it's an analog meter, so it's a little bit hard to read and get it accurately set. So what we're going to do is I'm going to use my plug-in energy monitor plug, and we're going to set this to voltage. And we're going to keep turning up the output from the VYUAN until we've got somewhere around 230 volts. Well, we're going to try and set it as accurately as we can. And throughout the test, as we start to load up our step-down transformer, we will constantly be readjusting this VYUAN to maintain this 230 volts. 230.3, I think that's about the best I can do. So this wire here, this is connected to the output, the secondary of our transformer. So what we need to do is we need to plug a load into it, and what I'm going to use an electric radiator that I've got under my bench here, and that's just a nice big convenient resistive load for us to use. So we'll just plug that in. And finally, we're going to need a voltmeter so we can actually monitor the voltage on the secondary of the transformer. So I'm going to use this Ryobi meter to do that, and we're going to set it to AC volts, and we're just going to use my def adapter connections here to actually stab into it and get the output voltage. Now finally, we're going to plug in our transformer to our VYUAN. So at the moment I've got the radiator under my bench switched off, so we're not going to be putting any load on the transformer. So we'll just switch the transformer on. And we're getting 115.4 volts out, and we're putting into it 230 volts. So what we need to do is we need to write down this, because this number is important for the test. So we need to write down 115.3 volts. So I'll do that. Now for the next part of the test, we actually need to switch our load on. So now that my step-down transformer is powering the load and providing current, you can see that the input voltage has sagged slightly in response to that. So we need to very slightly tweak up the VYUAN until we get 230 volts again. So if you look at the output voltage from the transformer now, it's actually dropped slightly. It's now at 113 volts. So what we need to do is we need to write that figure down. Let me switch off though. Now it actually takes far longer to write this down than it does actually to do the calculations. So our no load voltage that we recorded when the radiator was switched off is 115.3 volts. 115.3 volts. And we had a full load voltage of 113.7 volts. So we're going to divide that by our full load voltage again, which was 113.7, and then we're going to multiply by 100. 115.3 minus 113.7 equals 1.6, divided by 113.7 equals 0.01, multiplied by 100 equals regulation of 1.4%. Now for a transformer that's very good, but unfortunately we do have a slight fly in our ointment, which, as I started off by saying, that voltage regulation should be done at the full rated load of the transformer, which for this particular transformer I actually think it's probably 1000 watts. Well, unfortunately my radiator only presented a load of 500 watts, so we didn't actually do the regulation test at its full rated load, which is unfortunate. So I'm not exactly sure. I suspect that probably in the real world that would probably be 2 or 3% regulation if we could load this transformer up a little bit more. Unfortunately I haven't got another radiator, so now I've shown you how to do a voltage regulation test on a transformer, and you can actually do just the same thing on any type of power supply you build. So if you do build a power supply in the future, it's quite actually nice to kind of categorise its output characteristics, so why not do a regulation test? Well, another really important characteristic of our transformer that we need to look at is its power efficiency. However, when I talk about power efficiency, I'm really not talking about any kind of polar bear hugging, virtual signalling, Extinction Rebellion dick waving nonsense. Although I do admit the sight of Extinction Rebellion protesters being dragged off the roof of a train and being stamped on by angry commuters, that just never grows old, does it? So when we consider the power efficiency of our transformer, I'm actually really not that concerned about how much power it's drawing from the mains. What I'm concerned about is how much power it's actually wasting internally. And the reason that's a problem is because that wasted internal energy, it's going to show itself as heat. So if we've got a very inefficient transformer, it's going to get hot. Now, as we said earlier, our transformer is not a perfect inductor. It's a long length of wire, and that wire has resistance. Now, the formula for power dissipated is I squared R. So the more current we draw through our transformer windings, the more that the resistance is going to contribute to heat. So the more that we load up our transformer, the more the current will be flowing in both the primary and secondary windings, and that's going to exhibit itself as heat. Now, after our copper losses, the next most important source of losses are associated with the core of the transformer, and they can be split into a number of different types of loss. We can get circulating currents within the core of our transformer, and collectively these are known as eddy currents. Well, these eddy currents are another form of loss. Now, I'm sure when you've examined a transformer, you've seen that the iron core is made up of laminations. Well, the reason that the core is laminated, that's actually to help stop these currents, these circulating eddy currents. So they provide insulation between one lamination and the next to stop the current flowing. So that's what they're there for. We've also got another type of core loss, which is called hysteresis loss. So when we supply our AC supply to the transformer, the current magnetises the core in one direction, then the voltage reverses and the core is magnetised in the opposite direction. Now, at the point at which our magnetic field reverses, it takes a little bit of power to actually overcome the residual magnetism within the core, and again, that's what we call hysteresis loss. So basically all these losses add together and the end result is our transformer gets hot. So of course we don't want our transformer to get hot, so it's really important to try and minimise those losses, and a well-made transformer will have minimal losses. Let's find out if this is a well-made transformer. So we can use a simple formula to work out the efficiency of our transformer, and it's simply this: efficiency, that's going to be equal to the output power, and we're going to divide that by the input power. So unfortunately our transformer isn't a perfect machine. It does have some losses, and those are caused by the copper losses, which is a current flowing through the windings in the transformer, and also to do with the core losses. Now, because of these losses, we're not going to get as much power out of the transformer as we put into it. So let's just go ahead and just measure that. Now, as you can see, I've gone ahead and I've actually put this radiator on the bench so you can see what I've been using to do the testing, and we've got the radiator plugged into the 110 volt output from our transformer. Now really, when you're doing a transformer efficiency test, you do that test at the full rated power of the transformer, which for this one is around 1000 watts. Now unfortunately, we saw earlier, this radiator is only going to create a 500 watt load, so it's all I've got. So it's quite likely that the efficiency figures that we get, they're going to be a little higher than they should be. Now typically the efficiency of a transformer, we would expect it to be anywhere in the region of between about 92% to 98%. So you can also see that we're supplying our transformer here with power from the socket, and it's going through this energy monitoring plug, and I've actually got the energy monitoring plug to show watts. Now a lot of these plugs have a watt setting and a VA. Well, it's important for this test you want it set to watts. So at the moment we're actually feeding our transformer, which in turn is feeding the radiator. I can see here that we're actually feeding it with 557 watts of power. So that's our input power. So I'm going to write that down. 557. So I'm going to unplug this now. And I'm going to actually plug in our energy monitoring plug to the output from our transformer, because we're going to see how much power it's putting out now. So you can see that coming out of our transformer we're getting 535 watts. So again, I'm going to write that down. So you can immediately see here, as we would expect, we're actually putting more power into this transformer than we're getting out of it. We're putting 557 watts in, and we're only getting 535 watts out. Now a fraction of that power is going to be lighting up the LED on the front of the transformer case, but the majority of this is going to be going as losses within our transformer. So we'll just use my Casio FX31 calculator with its lovely fluorescent display, and we'll just calculate what the efficiency is of our transformer. So we got 535 watts coming out. We're going to divide that by 557 watts going in, and that equals 0.96, and because we want that as a percentage, we're going to times that by 100, and that gives us an answer of, I'll just show there, times 100, and that gives us 96.05% efficiency. Well, 96% efficiency, I actually think that's pretty good, but I think realistically our transformer might be a little less efficient than this, because as we said earlier, we haven't got it at its full rated load. We're actually only got it at half its rated load. But I did keep my hand on top of this transformer, and I had it running this radiator for about an hour, and the transformer hasn't even got slightly warm. So I think it has got a good transformer and a good amount of copper into it. So I think all in all, I am going to give this step down transformer a thumbs up. If you can just sort out the dubious nature of the electrical earthing on it, I think it's a good buy. So if we take our AutoTransformer here, you can see that we've basically got a big primary winding, and we've got a secondary winding which is just tapped off the primary. So all the primary winding it's just one great big coil of wire, and it's also got an iron core running through it. So basically, if we take a piece of wire and we coil it up, of course we all know that it forms an inductor, and in this case it's quite a big coil of wire. It's got many hundreds of turns on it, and it's got a big iron core, so we'd expect it to have it's going to have quite a high inductance value, you know, in an order of many millihenries. So this is going to be a very inductive load, isn't it? So if we just think about the voltage and current waveforms running in a coil of wire like this. So I'm just going to try and draw our voltage waveform, our incoming mains. I'm going to draw that in blue here, so we'll call that volts. I'm going to try and draw in our current waveform here, and yeah, I'm bound to get it slightly wrong. But the big thing about an inductor is that the current and the voltage, they're going to be 90 degrees out of phase, and that's really the definition of an inductor, isn't it? That the voltage and the current, they don't go up together. So again, if this was a resistive load, if we were putting power into a resistor, if we just actually draw the voltage in a resistor here, it would actually, that would be the voltage, and the current waveform would be in phase with it. It would exactly follow it. But in an inductor it doesn't do that. The voltage is out of phase with the current. So for our inductor here, we can see that our voltage actually leads our current by 90 degrees, and for a capacitor it actually lags by 90 degrees. Now there's a way of remembering whether it leads or lags, and again, everybody will probably know this, but I'm just going to tell you anyway how to remember it. So basically the way you remember it is there's a little rhyme which is Ellie the, and then it's Iceman, I-C-E, Iceman. So this is a bit that's important, the Ellie bit and the ice bit. For an inductor, the E, which is voltage, E is in front of I, so the voltage leads the current. Now for a capacitor, we have this ice bit here, so there's the C, so our current leads our voltage. So that's how you remember it, whether or not the voltages are leading or lagging. Just remember Ellie the Iceman. So basically we've just defined an inductor and its behaviour, and of course a transformer is just a great big coil of wire. So a transformer's obviously going to be very, very inductive, isn't it? It has to be, because it's just a really big coil of wire with an iron core. Well, I'm actually going to just show you something that might make you change your mind about that. So I've just gone ahead and I've plugged in our transformer via this plug-in power energy monitor, and you can see that we've got the energy monitoring plug. It's actually set to power factor. Now I know that some of you aren't particularly conversant with power factors. Well, don't worry about it. It's fair to say it is quite complicated, and if you understand it, the reality is you probably don't. Well, the definition of power factor is a ratio between true power and apparent power, but don't worry too much about that. I think a better definition is it's actually telling you what the phase angle is between the current and the voltage. In an inductor, we said earlier that the voltage and the current aren't in phase. At the moment, we're actually showing a power factor of 1.6. What's that got to do with the phase angle? Well, it's very easy to convert between power factor and phase angle. You've got a button on your calculator and it says cos to the minus 1. So if you type in the power factor and then press the cos to the minus 1 button, it'll come out as 80.7 degrees. So what that's actually telling me at the moment, our current and our voltage waveform feeding our transformer, they're actually out of sync by 80.7 degrees. Well, I did tell you earlier, didn't I, that the definition of an inductor is that the voltage was out of phase with the current by 90 degrees, and here we've just got a measurement of 8 degrees. Well, the reason that we get that is because there's no such thing as a perfect inductor. This transformer has got resistance in the winding, and it's also got an awful lot of capacitance in the winding, so that's all we're seeing. We're seeing a non-perfect inductor. So of course it's not out of phase by 90 degrees, it's only out of phase by 80. That's normal. That's what you should expect. However, we can actually think that if we had a power factor of 1, again, if you put the number 1 in your calculator and again press the cosine and minus, it will come out of 0. So if you've got a power factor of 1, it actually means that there is no phase shift between your current and your voltage waveforms. They're in phase with each other. Now, voltage and current waveforms which are in phase with each other, well, that's effectively the definition of a resistive load, isn't it? We no longer have an inductor. So what I'm going to do is I'm going to work some magic now, and you're going to see that power factor, you're going to see that change to effectively, it's going to become a power factor of 1. When it becomes 1, we don't have an inductor anymore, we have purely a resistor. So I'm going to work my magic, you just watch the display. So you can see we've now got a power factor of about 0.99 approaching 1. So if you take that 0.99, enter it into your calculator and then stab the cos to the minus 1 button, it'll actually give you a phase angle between your voltage and your current of just 8 degrees. So our voltage and our current are pretty much in phase with each other now, and I think you can actually see on the power meter it's actually swinging between 9.9 and 1. So effectively our transformer, it doesn't look like an inductor anymore, it's looking exactly like a resistor. Now the only time that transformers do actually resemble inductors is when they've got no load on them, and that's why it's important to actually have a transformer running at its rated load. Now in an ideal world I would like to have a nice big resistive load bank which I could connect to the output of our 110 volt step down transformer. Now I haven't got anything that's quite adequate, not that's variable in the kind of steps that we need, so I am doing something, I'm not going to call it dodgy, but I'm actually connecting the output from the step down transformer into the variac, and then the variac is actually feeding a radiator which is under the bench, which is a big resistive load. So effectively I can actually gradually turn up the load on our transformer. So what I'm going to do now is I'm going to wind up the variac, which is going to increase the load on the secondary of our step down transformer. And what you're going to see is you're going to see that the current waveform, it's going to start off being effectively 80 degrees out of phase, and then you're going to watch it and it's going to come into phase with the voltage, and at which point we've got a resistor. So I'm going to do that, and hopefully you can watch the scope and the power meter. So on the oscilloscope, the yellow waveform is actually the voltage. Now that isn't going to change, and the blue is actually the current that's feeding the primary of our AutoTransformer. So what I'm going to do is I'm going to get the variac, I'm going to increase it, and you're going to see that the current is going to get bigger, and it's also going to start to come into phase with our voltage, because at the moment it's out of phase by about 90 degrees. Now I know that the current waveform here in blue might not be looking quite like what you would expect. I think what we're seeing there, I'm not totally certain, but I think that these current peaks here under no load, I think that they're actually lining up with, it's when the core of the transformer becomes magnetised in one direction and then it gets magnetised in the other as the voltage changes. So I think what we're actually seeing is, I think we're seeing iron losses there. I'm not totally sure, but I think that's what we're seeing. Now I can't do this for very long because I'm actually overrating the stated current of this variac, but you can see now that the blue current waveform is pretty much in sync with the yellow voltage. So if I turn it down, you're going to see them go out of sync with each other. Can you see it's moving away? And now it's moving back towards it as I increase the load. Now it is probably worth me saying that I'm not saying that transformers are the same as resistors. Actually, it's probably more true to say is that the input to a transformer in terms of its power factor will actually reflect what its secondary load is. So if you've got a resistive load and you actually load the transformer up to its rated current, it's going to look like a resistor on the primary side, whereas it's more conventional for us to have maybe a transformer in the power supply. It's usually feeding a very big bank of capacitors, so of course it's going to look like it's got a quite poor or awful power factor, but that's not really the transformer's fault. That's because we've got a great big bank of capacitors connected to it. Christ on a bike, it's John Ward at the door. Well, until next time, I think that'll do. Bye for now.